Hello and welcome back to the module Calibration of Industrial Robot Systems. In the last class we studied fixed tool calibration, in which we studied about external TCP and workpiece calibration. Those were mostly static systems and they were not controlled by the robot controller. In today's class we'll further extend calibration of industrial robot systems, in which we'll be doing base linear track and external turntable, which are also known as rotary axis. These are dynamic systems that extend the degrees of freedom of the robot and are controlled by the robot controller itself. Okay, so let us start. So the calibration of base linear track, how does it look like? You just see a robot is no more grouted permanently to the platform on the ground. Rather, these are mounted on a linear track, just like a railway track. Okay, that also has provision to cover all the cables and transport all the cables along with the motion that it can do. Okay, these are not static systems. Rather, these are like just very much like prismatic joints, which can move the base of the robot, on which whole of the robot can also move. Okay, so let us just see a quick video that will demonstrate it well. So this is a robot. You see it is mounted on a linear wheel. It is moving, the base, whole of the base is moving, and on top of that whole of the robot is also moving. These are meant to basically extend the workspace of the robot. A robot, let us say, it can go to certain within its reach of the arm. If the base itself moves, it further extends that reach. This is a huge robot, that is KUKA KR1000. That's a Titan robot of almost 1 ton payload capacity. It is doing wood stacking. Okay, hope you got it. So let us continue further. So yes, the linear tracks are self-contained actuators. They are themselves are actuator. They are mounted on the floor or on the ceiling, or it can be on the wall also. So that has provision just like a flange on which your robot can be mounted. Okay, so the motion is synchronously controlled along with the other axes of the robot. This controller also has provision to attach an external axis, so this becomes one of the external axis also. So the motion is synchronously controlled by the controller along with the other actuators of the robot. Okay, the frame L is attached. So let us just start putting the nomenclature here. So I am calling the linear rail as a frame L, which is attached to the linear track, which is fixed and aligned to the world frame. Okay, the frame attached to the robot base, we will call it as R, is a dynamic system and moves on the linear track. So this base frame of the robot, that is R, that will move on top of the linear rail. Okay, so there exists an orientation transformation that we will call it as LQR. Q is the error matrix, that is the orientation error matrix between L and R. Normally we try to put the robot frame aligned to the linear rail frame, but it is not always possible due to some manufacturing defects or mounting defects, some other errors between the linear rail frame and the robot base frame. So that is what is LQR will assume. So what are the assumptions that we'll put here now? The robot moves along the x-axis of the linear track. So and every displacement that we can make to this linear rail, so robot will be displaced by the same displacement, and I am assuming it is moving along the x-axis of the linear rail. My second assumption is there is no translation of the robot along y and z axis. Okay, in reference to the linear rail, there is no offset along y and z axes. And x, if it is there, it is only the active displacement which is actuated by the linear rail joint. Okay, it is very much like a prismatic joint. So steps for calibration: finding the unknown, that is LQR, that is the orientation error between the L and R frame. So that is what is our job now, that we'll do in this calibration. So during calibration, the TCP of a pre-calibrated tool. So there is a tool which is attached to the robot's tool flange, okay, and it is already calibrated. So wherever the tip of this TCP will go, tool center point will go, will quickly know the location of that TCP by robot's forward kinematics. So this tool flange, calibrated tool, will now be moved thrice to any fixed reference point in the robot workspace. So there is a fixed reference point in the robot workspace. So this robot is now made to touch from 3 distinct directions to the same location. So the position of the robot on the linear track from L is recorded, that is x, that is the displacement which is here. So it can be x1, x2, x3, like that. So that is recorded. The controller uses these data to calculate the unknown orientation, that is the error matrix LQR. So this is what is this calibration is all about. Okay, so the 3 contacts should be made from 3 distinct directions. They should not be very close to each other. That will cause later on, when you will see the calibration approach for this, you will find that it is going to create some sort of singularity. Okay, so you won't be able to get to the solution. So that is why this is warned at the very beginning of the calibration step. Okay, so let us now analyze the calibration of linear tracks. So how does it work? So you see what you did now, you simply approached it from one of the locations. So what exactly you did? You moved it along linear displacement along the linear rail. The base has moved by a distance x1 from L. So L to R, linear displacement along L, along this x-axis of the linear rail is x1. Okay, from R to TCP, from R to TCP, that is the distance which is quickly obtained by the robot forward kinematics. That means the TCP position with respect to the robot base as well as its orientation of the TCP can be quickly obtained using robot's forward kinematics. Okay, so because this is already a calibrated robot, so you quickly can obtain the TCP location, that is F1 vector can easily be obtained, but in robot's base frame. Okay, now this is your R. What is R? R is the unknown, that is because you know this fixed tool which is there as a reference, which is kept outside the robot in the robot's workspace, is free to move. Okay, you can search, you can find any good place to touch your TCP from different locations, 3 different locations. So this is an arbitrary reference point. Okay, so during the closed vector triangles that was established upon making contact with external reference point. So you see robot was here and using its forward kinematics it touched upon this point. Robot is now here, forward kinematics reached here. Robot was again here, forward kinematics is reached here. So it every time you can obtain F1, F2 and F3 in robot's base frame, R1, R2 and R3 locations. Got it? R is an unknown. Okay. X1 and X2 and X3, these 3 are distances from L. So that is in frame L. If you call it a vector, if this is a vector which is represented in L frame, so it is X1 0 0, X2 0 0, X3 0 0. It can be expressed like that. So you can quickly write it like this, 3 different equations. Let me explain just one of them. You see what is happening here. So this is, you just pick up any one vector triangle. Let me wipe it off a bit. Let me just take one of these triangles. So see what is happening. So R is sum of x1 vector and f1 vector. But you see f1 is in this frame, whereas x1 and r is in this frame. So from here to here, you know there is an error. Okay, so there exists an orientation error. So let us suppose you have a transformation matrix that gives you that orientation transformation given by LQR. This is an orientation transformation from L to R. Okay, so multiplied with LQR, now F1 will be in L frame, that is linear rail frame. So that is what I am doing. So this is in linear rail frame. This also is in frame L. This also is in frame L. So altogether this is a closed vector triangle equation, and same for all the three instances that you did. That is from here, and from here. Got it? So R is nothing but it is the vector joining the frame L and the fixed reference point. This is the tip of this reference tool. Okay, F1 is a vector joining the frame R to the fixed reference frame expressed in frame R. So F1 is in frame R. Got it? So these are the two important elements which are here. This is what we have to find out. Okay, F1 is obtained using forward kinematics. Magnitude of F1. Direction of F1 is in R frame. If it is obtained from forward kinematics, you get it in R frame. But multiplying with transformation matrix from here to here, you can get it in L frame. That is what we did. So x1 is position of the robot on linear track. Okay, position on the linear track. So it is simply x0, 0. Okay, so it can be written like this. Okay, so copying back these three equations that we have obtained, let us move ahead, cyclically subtracting these. So this minus this will give you the first one. Okay, then this minus this will give you this one, and then you have this minus this will give you this one. Got it? So that is how it is obtained. So you got three equations and they are independent of R. So you see this R has gone. That is something which is unknown. So it has been eliminated here. Now you are left with this that is known through forward kinematics. This is known because you are displacing the robot on the L frame, that is linear rail frame. So you know this already. This is something which is unknown, and that is there in all the three equations. Okay, so let us put that in compact way like this, that is in matrix form. So I can quickly write it as taking this common. So this is here, this is here, this is here. That is one full matrix, and similarly you take it on the other side, you are remaining with a negative sign here, and again those are put like this. So x, any vector x is x0, 0, scalar values are there. Similarly forward kinematics will have fx, fy and fz. So that is 3 cross 1 vector. So all aligned in this way. This is a 3 cross 3 vector. This is also 3 cross 3. Orientation error is also 3 cross 3 vector. So it is like this. Got it? So you see, now you can write it at, you just take inverse of this, multiply to the both sides of this equation, you will get LQR as this. So you have obtained the orientation calibration matrix. That is nothing but orientation error that is there between L and R frames. So that was our objective and we have obtained that. Got it? So it is quite trivial. Now you are capable enough to handle any external TCP point. Okay. So now the end effector TCP in frame L may now be calculated as this. So you can simply calculate any point F which is in this frame. Okay, you can now get that point in this frame. Okay, so if you reach to TCP using your robot, So you have this. This was something that we have identified just now. This is the linear displacement that is there. So now the same point is this one. Got it? So this is equivalent to R as we have just seen. So for any instance I, you can quickly find out the location of this tip of your robot in L frame. Got it? So the end effector TCP orientation in frame L is L to R, R to TCP. So effectively what you will get, it is L to TCP, that is orientation of the TCP in frame L. Okay, so this is your orientation, this is your position. Got it? Okay, the inverse kinematics. Let us say I want to go to some position given by Pi. So how to reach there? You simply know, using same equation I have obtained this. So this is what is to be done using inverse kinematics. So you have obtained Fi. This vector is now extracted out, and using this, if you already know how much is the orientation that you want, L to TCP, so this was your calibration matrix. So you got what? R to TCP. So TCP orientation with respect to R. So that becomes the input for the inverse kinematics algorithm. So you know the orientation and position in frame R. So that is what goes to the inverse kinematics algorithm, and you can do inverse kinematics. You can calculate the joint angles to reach there. Got it? Now that we have assumed X over here, whole of this system can be assumed like a 7 degrees of freedom robot, and you can express them in DH parameters, and you can do forward kinematics as well. That is quite easily possible, but normally in industry it is trend to use this as X. That is the reason I have taken it as X. Otherwise you are free to choose it as X, Y or Z, whatever is okay. Normally in case of DH you should take this as Z axis. You know that that is a prismatic joint. So this can be your prismatic joint. First revolute joint will be moving on top of this. So that is quite easily possible. So how many number of solution does it have? This inverse kinematics, now it is a 7 degrees of freedom system. 6 within this robot and plus 1 from this linear range. It is a 7 DOF system. What you can attain is a 6 DOF, that is 3 for translation and 3 for orientation. So it should have redundant solution. So how many solutions does it have? Just look this carefully. You see, this equation is possible to have a solution for every value of X. So in order to go to a particular position for any value of X, if it is within the reach of the robot, so whatever is the value of X, you should be getting F, that is the TCP position with respect to the robot base, and it is solvable. It is it has 8 different solutions for each F1. So that is quite easily possible, and this orientation also. So your orientation changes with respect to the robot, but your orientation may be stable with respect to the linear frame, L frame. Okay, so your robot will move, but your L frame will, your TCP orientation will not change. With respect to the R position, it changes, but it doesn't change with respect to this frame. So hope you got the insight of this. Now let us move ahead. Okay, so now we'll be doing calibration of external kinematic system. To begin with, we'll do turntable, that is also known as rotary axis. So how does it look like? It looks very much like this. You have an axis which is placed outside to the robot. It is grouted to the ground. Okay, it is fixed. This tabletop can rotate. So it has an axis about which it can rotate. Okay, and it has a location also through which it passes through. If at all it is a circular disc, so that should be the center of the circle, and there is an axis, okay, about which you can measure the angle of this rotary disc. Got it? So let us quickly see the video again. So you see, this is one of the application which is of CNC machining, which a robot is doing. So KUKA robot again. Is doing its job nicely, you see. So whole of the system needs to be calibrated. You should know where is the center of this tabletop and also the location of this table with respect to the robot in order to express them in robot's frame. So that is what is our job. So if this is your R frame, you should know where does this center of this tabletop turntable is located. Okay. So let us begin. So this enables the robot to move with a kinematic coupling to the external axis. As I told, this becomes the 7th axis and that goes to the controller also. So controller can now include this information also to its kinematics and it can control all of them synchronously. Okay. So what all things that goes on here in calibration for such an arrangement is the calibrating the root point. Root point is the point which is located at the center of this turntable. Okay, so what does it include? It basically includes the vector that connects this. You should know this vector, where it is located, position vector of the center, as well as orientation of this tabletop. If this is your orientation, you should know how is this axis aligned. Okay, so this job is basically done by root point calibration, and second one is workpiece frame calibration. If at all you have an object which is kept on top of this, so the center of that with respect to this should also be known, because you have to machine on this. So that is on this frame, it is not at the frame which is located here. So that is the second job that we will be doing. And if at all there is a tool which is there on rotating external turntable, okay, so that also can be taken care of. That is very rare, but that also is one of the job if at all you have a tool in the workspace which is mounted on top of this rotary axis. So anyway, let us move ahead quickly. So calibrating the root point of the turntable, how it is done? The TCP of a pre-calibrated tool on the robot. Again, you have a TCP which is mounted on top of the robot's tool flange and it is calibrated. TCP calibration is done for that tool, is moved to the reference point on the turntable from 4 different directions. Okay, so your robot is made to touch over here, over here, over here and over here. 4 different locations. So you make your turntable rotate, make your TCP go there, again rotate, go there, again rotate, go there, like that. Do it for 4 number of times. The position of the reference point is kept different at each time by rotating the turntable axis. They should be very distinct. Again, you should be very careful. Your solution should not go singular, so they should be very much different. Okay, and TCP locations and the rotary axis positions are recorded. That means the angle that it has turned, you have to record that. Okay, that is recorded. And TCP locations, so wherever your robot is going, that you know, if it is pre-calibrated tool using forward kinematics, you can calculate where it has gone. So all the 4 locations you will record. You will also record the angle that it has turned by going to those 4 locations. The controller can now calculate the root point of the external axis. So that is what is our job. Let us do it. Let us analyze how the controller does it. So analysis of the root point calibration of the turntable, which is also known as rotary axis. The TCP of the pre-calibrated tool on the robot is moved to the reference point on the turntable 4 times. You know, they are 4 distinct points. Turntable are recorded in static frame B. So this is the frame which I have put here. Okay, and this is a static frame about which your turntable is rotating. So turntable rotates about ZB axis. About this axis your turntable is rotating. Okay. Assuming the reference points are at a distance r, so if at all you are touching upon the same point at every location of the turntable, okay, so r is fixed. So this distance is fixed from the center, okay. It is moving about the axis ZB and subtends angle theta I from x. Let us say your reference frame is posed like this, XB, YB and ZB, that is the B frame which is over here. So you are measuring theta from x axis of the frame B, okay, in plane XB, YB. The points can be written as I is 1, 2, 3, 4 because there are 4 instances. So points may be written as P1, P2, P3 and P4. Those are the points. Each of these points are r cos theta and r sin theta and 0 because they are on the plane with respect to this turntable. So z is equal to 0 for all of them. But because theta is varying, your pi's are varying. So you have 4 different pi's which are here. So making it compatible with other homogeneous transformations that I am going to use, I am putting 1 over here so that I can handle it with homogeneous transformation matrix. Okay. Okay. These 4 points are known in which frame? It is in frame B. Now what the robot was doing. So whenever the robot was going to those 4 locations, so it was also recording those points in its own frame. So in its own frame, if you take this point to those 4 locations, so you will get that these positions in R frame as well. Let us just understand what are the unknowns which are here. First unknown is this, that is the position vector that connects the R to frame B. Okay, that is given by Bx, By and Bz vector, which is here position of frame B in frame R, and also this orientation error which is there, that is the orientation matrix of the frame B with reference to the robot's base frame R. That is a 3x3 orientation matrix. These two are something that we have to find out by this calibration. Okay. So now the robot combined transformation matrix from here to here may be given as this. This is your orientation change. This is your position vector which takes it from here to here. Got it? So this is your transformation matrix that takes it from here to here, R to B. Then the same 4 points are also recorded in frame R. You know, using forward kinematics, you can obtain all those F's. Okay, so F1, F2, F3 and F4 are 4 locations that you have recorded, and again making it compatible to homogeneous transformation matrix. So these points are again in frame R. So earlier it was in frame B, this time it is in frame R. Got it? So now relating both of them, the points in frame B and frame R may be related as these are points in frame B, this is point in frame R. So here goes your transformation matrix which is unknown, which is to be found out. So you can quickly write it as this. So this gives you the end result. Got it? So this is your calibration matrix. So it has 2 components in it. So it has first thing, that is the position of B and orientation of this of frame B with respect to the frame R. So that is there in this. Okay. So any point now, if it is in frame B, can be expressed in frame R. So if it is with respect to frame B, so you can express that using this. So this is the same old equation that I have used just previous slide. So it is this one. So this is all you can obtain. Okay. So any point F1 which is moved by the robot can be expressed now in turntable frame. So if I am taking my robot somewhere, I want to know where it has reached in with respect to B. This can be calculated using this. So just rearranging this same equation, I can obtain this. Got it? So forward kinematics, F1 vector is known, B is known through calibration. These two are known through calibration. So you can obtain this. So any point where this robot is going, you can express it in B frame. Got it? So this is what was our job. Now let us put a workpiece on top of this turntable. Okay? And whatever I know, I have complete information about that workpiece. So each and every point on this workpiece is known with respect to its own frame, but not with respect to the turntable on which I have kept it. Okay? But I have to machine it from different sides. I have to machine it from different sides, the way it was doing. Okay? So you see, there must be some offset between the frame B and the workpiece frame. Okay? So that offset now is to be determined. That offset will be in terms of displacement as well as orientation. So that is what is the workpiece frame calibration. So this will enable handling of the point that are defined with respect to the workpiece, which is fixed on the turntable. Okay? The offset in translation and orientation of the workpiece frame with reference to the turntable frame is to be calibrated. Okay, so that offset needs to be known. By default, if at all you don't calibrate it, you have to work with the existing frame which is there, and all the points needs to be addressed with respect to B, so that you can express it with respect to R and your robot can reach there. How do we do it? The TCP of the pre-calibrated tool, this is again a pre-calibrated tool, that tip is now moved to the origin. Wherever you want to make it as an origin of this workpiece, you have to take your robot there and two other points on the desired workpiece frame. So, okay, the controller now is able to define the workpiece frame. So let us analyze that. So setup for that will be the pre-calibrated tool is mounted on the robot, this one, and the root point of the turntable is also calibrated. That means this point position as well as orientation with respect to R is now known. Now I will mount the workpiece on top of this. So in the first step, the TCP of the robot is moved to the origin of the workpiece. So the origin of the workpiece in frame B is evaluated using our earlier formula that we have handled. So this is obtained using forward kinematics. Wherever my TCP is going, because it is a calibrated TCP, so I know F1. This is a calibrated root point. So this position of this with respect to the robot's base is known. So this is known. Got it? So this vector is known also. This is the calibration matrix for the root point that we have obtained. So I can now know the position of this point. I call it as P1 with respect to B is now known. So I'll quickly obtain this vector. Got it? So that goes, this is nothing but this one. Got it? So that is what is obtained. So current position of the TCP in frame R is obtained using forward kinematics. So in this case it is F1. Now the second step. So the TCP of the robot is now moved to the point on the positive x0 axis of the workpiece. So anywhere along the x-axis, wherever you want to make it as x-axis of the workpiece, you touch it somewhere on that axis. Okay, and again you calculate your next point, that is this one. Where is that? It is this one. Okay, so it is in frame B, which is attached here. Okay, so this is your P2. Okay, and what is that? It is nothing but again you calculate the TCP point F2 vector, and B is known, you know, B vector, that for this it is already known. Okay, and orientation calibration matrix for the base frame is known, B frame is known, turntable root point is known. So you can obtain this. Okay, again I'll use this further and calculate a vector along x-axis, because you have already known this point with respect to B. Also the point which is here with respect to B, taking the difference, you get a vector along x-axis, positive x-axis. Okay, so this is your U. Mind it, this is all in frame B, because you have expressed all the vectors in frame B. Okay, so this is your U. So unit vector along x0 axis will be, this is your x0 axis, is x, that is U by magnitude of U. Okay, again in step 3 the TCP is moved to any point with positive y value on xy plane. So this is the top. So this is already your x-axis, this was your y-axis. So you have to go somewhere over here. So a line which connects the origin to this is your v vector. I am taking it as v vector. This was already known. Okay, that is P1 was known in frame B. Okay, so now use all these informations. So the point on x0 y0 plane on the workpiece in frame B is known using this same old formula. So again V can be calculated using P3 minus P1. So this, the third step, this location is P3 in frame B. P3 minus P1 will give you this vector. So that is what is obtained here. Okay. So now you know, we did it earlier also similar while we were calibrating the external reference plane. Okay. So same thing we are doing here again. So a vector W is given by, W is nothing but it is a vector which is aligned to Z0 axis in frame B, that can quickly be obtained by taking cross product of U and V. So they are lying in the plane XY, so it will give you a vector which is along Z0 axis. Okay, I call it as W. So I have obtained W. So unit vector W will be Z. It is a unit vector along Z0 axis given by Z is this. So you have obtained unit vector W. You already know unit vector U. So you can obtain unit vector along Y axis also, that is given by Y is equal to Z cross X. So all the three unit vectors are now known. That means this frame W is now fully defined with respect to B, because all the vectors are in frame B. Okay. So now the origin of the workpiece in frame B is this one. First time where you have touched, okay, you calculated what? You calculated P1 in frame B. Again, the orientation is given by B to W. So you already have X, Y, Z in hand. You can quickly write it as this. So this is nothing but orientation of workpiece frame with respect to B. This is by definition of rotation transformation matrix, you know it. So now any additional transformation Q due to rotation of the turntable by an angle theta about Z0 is, this is an additional rotation transformation. This is nothing but rotation about this by an angle theta. So this is your additional transformation. Okay. So this is to be included. You can now express any point which is on this, any point which is represented in this frame to this frame. If you know it in this frame, you can express it in robot's frame. Okay. Additionally, if you have further rotated it by an angle theta, the turntable rotates, then you can additionally include this. That is, you have to pre-multiply the points to this rotation matrix. So whatever you are doing with this, additionally you have to do this transformation. Okay. So effective dynamic position, that is position and orientation of frame W in frame B, is calculated by pre-multiplying with QT. Okay, so this is how you can handle any rotating axis if it is there in the workspace. Okay, so you have now seen a linear axis on which robot can be mounted. You have now seen an external axis too. Okay, that is a rotary axis in the workspace. Okay, so that's all for this module. In the next module, we'll study robot statics. So we'll deal with link forces, moments, gravity compensation, force, velocity, ellipsoid. So that's all for today. Hope you are enjoying. Thanks a lot.